So what is electrochemical activation? And in fact, this is nothing new. I mean, we've been drinking here in the UK water which has been treated with chlorine for well over 100 years. And in fact, that's probably one of the biggest, largest single public health interventions in the 20th century. So electrochemical activation has been used extensively in the water industry for producing chlorine which we use to dose mains water supplies, and that makes our water supplies nice and safe. What we've done with electrochemically activated solutions is adopt that technology. Obviously we're using better materials, we're using better technology to compartmentalize that in a way that can be used in the home or in the workplace. And electrochemical activation works by passing a very weak salt solution through two electrodes. And those two electrodes, albeit made of quite complicated surface materials, which provides a lot of the necessary science and reactions to give rise to that antimicrobial solution, those electrodes essentially help produce the solutions that are so effective. And this is quite a well understood and well known property called electrochemical cells. So essentially all the solutions that are produced, which we call electrochemical activated solutions, are produced in these electrochemical cells, and they're a little bit like batteries. What is unique about some of these systems are the materials by which these electrodes are made, and also the electrolytes that are used. So in many systems, the materials often are made of a whole range of elements and metals, which could be rubidium oxide, titanium oxide coated surfaces, and an electrolyte solution, which is essentially sodium chloride, a weak brine solution, is passed through these two electrodes. Those two electrodes have a potential applied to them, and that energy that's inputted into the electrochemical cell then kickstarts a whole range of reactions that occurs at the surface of the electrodes and between the electrolyte that passes through those electrodes. So many people would say, well, so what? Well, what happens in that cell is you get a lot of chemistry, and you get the formation of a lot of chemicals and radicals and sort of excited ions that give rise to antimicrobial properties. So for instance, what produces the disinfection in relation to bleach? Well, we know that is chlorine, but actually it's not just chlorine, it's the reaction that chlorine has in the water, and the resulting products, chlorine related products, provide that kill. In electrochemical technology, you for sure have chlorine products, but you also have other products related to water, so a lot of OH minus products. And essentially you end up with what I would like to call or term a little soup of reactive ingredients that really want to attack organic material, in our case bacteria, because they need to. Chemically and physically, they need to react. So we're creating a whole soup of excited reactant products, and those products are really useful. The nature of those products is such that they are can really only react with bacteria, and they can interfere with the membrane wall, and that interference in the membrane wall results in the death of the bacteria. Now, of course, this is happening at a very small level. In our world, we're applying that on big surfaces, we're applying that maybe even on food or in water. But the net result is the same. You get the interaction of your antimicrobial or your disinfectant with the bacteria, and that causes a disruption in the cell membrane, and that ultimately kills the bacteria. And in the research that we've done, this is universal. So all bacteria are subject to this interference when you apply electrochemically activated solutions to the bacteria. And this is nothing outstanding in that sense. It is a very common mechanism by which many disinfectants work. And this is how ECAS works.